All right, we are going to talk a little bit for this week 3 office hour about vectors, and we are going to we're going to give ourselves a set of vectors, and then we're going to ask some questions of them. So I'm just going to draw out these guys like this, 0, 0, 1, 1. So let's say this is our collection of vectors. And the first question we want to ask is, are these vectors a basis in our 4-dimensional space, 1, 2, 3, 4? All right. And in order for these vectors to be a basis, they need to be linearly independent. Now, what does it mean to be linearly independent? Well, if you had linearly dependent vectors, then you could scale linearly, of course, the vectors that you had, and you would get back one of the vectors in your collection. That would be, in this case, vector 4 would be linearly dependent on 1, 2, and 3. All right, so if you can't ever make this happen, then you have linearly independent vectors. So that's what we want. Now, a quick inspection of this shows us that if we subtract the second vector from the first vector, we get back the third vector, and so unfortunately it is not a basis. We can do this out if you want. 1, 0, 0, 0 minus 0, 1, 0, 0, and this is all, you know, vector matrix style arithmetic. 1, negative 1, 0, 0. All right, and so you see that this is unfortunately not a basis. All right, we can ask another question. We can ask, are these vectors orthogonal? Right? Now, in order for vectors to be orthogonal, their inner product, which is, and we'll talk about this in a second, their inner product needs to be 0. All right, for all the vectors, so for all the combinations of vectors, you could do multiplication and inner product, and they'd be 0. Now, the inner product is a pointwise multiplication and sum of every entry in the vector. All right, so let's take an example, and let's do v1, v2, right? And that's it's going to be 1 times 0 plus 0 times 1 plus 0 times 0. Hey, that's good news, right? Great. So let's do v1, v3. And that's 1 times 1 plus 0 times, oh, well, that's too bad. Equals 1. So, not orthogonal either. Well, we can ask the question, although I'm not exactly sure why, we can ask the question, are these vectors orthonormal? All right, so what does that mean? So orthonormal vectors are a subset of orthogonal vectors because you have the orthogonal rule, but you also say that when you take the inner product with its own self, that you get back 1. All right. Now we know that they're not orthogonal, so they're not orthonormal either. But I want to point out also that these vectors don't have a norm of 1 either. So, for example, v4 and v4, right? That's going to be equal to 2. Right, so that is not 1, and so these are not normalized vectors either. So this is a not great set of vectors to choose, but that's okay because there are plenty of linearly independent vectors in our 4 collections of 4 vectors that are linearly independent, are orthogonal, and even some of them are orthonormal. And I encourage you to find some of them. That's it.